So in this video, I'm going to tell you about the importance of the t-distribution in statistics. So this is a follow-on video, and I apologise for the sound of the motorbike outside that will pass. This is a follow-up video for my video on the importance of the chi-square distribution, which I put in my probability and statistics playlist. So please watch that one before watching this one, because a lot of what we do in this video is going to depend on things that I discussed there. So we're basically going to take the content of that video and go further with it to discuss the importance of the t-distribution and how t-tests work. So firstly, I think I'll just start off by reminding you of the way in which the t-distribution is constructed. So hopefully you're already aware of this, and ideally you would know the PDF of the t-distribution, or at least have some idea of the PDF of the t-distribution, know about its shape, and certainly know this definition that I'm about to write down now. So let's say that we have a random variable z that is standard normally distributed, so normal 0, 1, and let's say also that we have a random variable v, which is chi-squared distributed with n degrees of freedom. So these are quite common symbols used. Z is quite commonly used for standard normal, and v is quite commonly used for chi-squared. And then let's say that we take z and divide it through by the square root of v divided by its degree of freedom n. And let's call this new random variable, we'll call this random variable x. And then the question is, how is that distributed? Well, that ends up then being t-distributed. Oh, I should say also it's important that z and v are independent. So I'll write that down. So z, v, independent. Then x will end up being distributed t with n degrees of freedom, so the same number of degrees of freedom as the chi-square distribution that was in the denominator here. I think I'll also remind you of the PDF of the t-distribution before we actually get on to the bulk of the video, which is understanding how this is actually important, how t-tests work. I'll just remind you of the PDF of the t-distribution. I have a video in which I go from this definition of the t-distribution to the actual PDF. It's quite a long, extensive exercise, that derivation, so I'm not about to repeat it here, but if you would like to see how you can go from this to working out what the PDF of this random variable would be, it's in my playlist on statistics. So PDF then, so the support firstly for the t-distribution is the entire real line, so little x can be any real number, and the PDF then of big X as a function of little x for this t random variable is, and this looks a little bit scary, don't be scared by it, but it does look a little bit scary, so gamma of, let me make sure I get this right, I think it's n plus 1 over 2, and then over the square root of pi times n times gamma of n over 2. Now, even though that looks incredibly scary, this is all actually just a constant out the front. You know, there are no x's here yet, so this is all just a constant. Once I tell you what the degree of freedom that I'm working with is, I can plug it in here, and yes, it's a complicated function, the gamma function, but it is some value, that's just some number. Square root of pi times n, again, it's a complicated number, but it is just a number. And then gamma of n over 2 is also just a number. So this is all just some fancy constant that is needed in order to make the area underneath my PDF equal to 1. And then we've got 1 over, and here's the bit that actually has x involved. So it's 1 plus x squared over n to the power of n plus 1 over 2. That's the PDF for the t-distribution on the entire real line. Now, it does look a little bit complicated, so let's just, to get some intuition, let's just look at t1. So let's say that x is distributed t with 1 degree of freedom. Then this massively simplifies, so the PDF is now going to be, let's plug in 1 for n, so we get 1 plus 1 is 2 over 2, so that's gamma of 1, which is 0 factorial, which is just 1, so that's very simple. Then here we will get the square root of pi times 1, so that's just the square root of pi. And then something a little bit more complicated, gamma of a half now. So that's something that, again, we could derive, but I'm not going to do it because it's a bit of a long exercise. It's a very, very famous number, gamma of a half. It's equal to the answer of the Gaussian integral. So there's an integral for this. So this, by definition, would be the integral from 0 to infinity of, and then it's u to the power of the alpha minus 1, which is half minus 1, so we get u to the power of minus a half e to the negative u du. So that's the integral you'd have to perform to get what this is equal to. But this is actually an equivalent integral to another very famous integral, which is the Gaussian integral, which is the integral from negative infinity to infinity of e to the negative u squared du. You can show for a reasonably simple substitution that these two are equivalent to one another. And hopefully you know what the answer to the Gaussian integral is. It's the square root of pi, so gamma of a half is also the square root of pi. So both these integrals are equivalent. It's not too difficult a substitution to show they are, and their answer is the square root of pi. So anyway, that was just a long way of saying that gamma of a half is the square root of pi. And then n is equal to 1 here, so we get 2 over 2, 1. So this becomes just 1 over 1 plus x squared, so much more simple. So it's just going to be 1 over pi times 1 plus x squared is the PDF over the entire real line for T1. And you can see that these other ones, these where n isn't 1, they're just kind of more complicated versions of this. You know, you get the n here, you raise this bit to some more complicated power here than just 1, and you end up with some much more complicated coefficient in order to you know, normalize this distribution. Well, not, I don't know whether normalize is the right word, but make the area underneath it 1. So actually, looking at this one, T1 is going to give us good insight into what the others look like as well. So if we just think about trying to draw this graph, and you might already know this, what this graph looks like from calculus, because it's quite a famous function in calculus. So if we think about what it is at 0, x is equal to 0, forget the pi for a moment and just think we've got 1 over 1 plus x squared. The pi is just there, the 1 over pi is just there to make sure that it integrates to 1. So if x is equal to 0, then this is just going to be 1 over 1, and then we will put the pi in, so it would be 1 over pi here. And then as x gets bigger, you know, if you go this way, you're going to be dividing by a bigger and bigger thing here, so you're going to get smaller and smaller and smaller. And equally, if you go this way in the negative reals, again, when you square, you're just going to get a positive number. So this denominator is going to be getting bigger and bigger. So it's going to be symmetric. It's going to be an even function, and it's going to actually look something like this. And now I'm going to not do a good job of making this look symmetric, but never mind. And it's basically a bell-shaped curve. It looks very like the normal distribution. Indeed, all the t-distributions, they have this same sort of bell-shaped pattern. And in fact, interesting fact that I am not about to prove, but something that you should know if you're if you're a keen statistician, is that if you let n tend to infinity, this distribution, the t-distribution, tends actually to the standard normal distribution. So Tn tends to normal 0, 1 as n tends to infinity. And that's why, you know, if you have a t-table, one of those statistical tables, and you look at the, say you have the t quantiles, and you look at the infinite degree of freedom, so there is an infinite degree of freedom row usually in those t-tables. And if you look at that, those quantiles will be the same as the standard normal quantiles if you compare them to a standard normal table, quantile table. So even if you're not given the standard normal tables, it's interesting to know, because I have had statistics exams where they didn't give you the standard normal table, but you can work out what you need to know, which is the standard normal quantiles from the t-table. So that's interesting to know. So for example, if you look at the t-infinity row of a t-quantile table and look at the 0.975 quantile, the 97.5% quantile, this will equal the standard normal, the Z 0.975 quantile, and hopefully you know what this number is. This is a very famous number, but just in case you need a reminder, it will come out as 1.96. So either you can see that in a quantile table for the standard normal, or you can go to the quantiles of the t-distribution and look at the infinite degrees of freedom row, and you'll see that it matches up. Okay, so what else would I like to say before we actually get onto the bulk? I might just point out that going back to this T1 distribution here, this function 1 over 1 plus x squared, this is a classic calculus problem. This is something that has a beautiful antiderivative. The antiderivative of 1 over 1 plus x squared is the inverse tan function, so it's arctan. So if you differentiate arctan of x, it will give you 1 over 1 plus x squared. Therefore, if we wanted to integrate our PDF 1 over pi 1 plus x squared dx from negative infinity to infinity, this will come out as, we'll pull the constant out, so 1 over pi, and then 1 over 1 plus x squared integrates to arctan of x, and then we'll be evaluating between negative infinity and infinity, and then if you evaluate arctan at infinity, that will be pi by 2. If you evaluate it at negative infinity, that will be minus pi by 2, so you'll get pi by 2 minus pi by 2, which will add together to give pi. The pi will cancel and you'll get 1. So indeed, it is a PDF. It integrates to 1. It's always positive. And this is what it roughly looks like. And these ones are just more complicated versions. They still look like bell curves, just slightly modified. So all the t-distributions are these symmetric bell curves, similar to the normal distribution, and as you tend the degrees of freedom up to infinity, in fact, it tends to the standard normal distribution. Okay, so there we go. That's a little bit of a reminder about the t-distribution. Now what I want to tell you is why it's so important. Why are t-tests so important? Why do t-tests work? Why does the test statistic that we have in t-tests come out t-distributed? So this is the setup then that I'm going to take. I'm going to do a little hypothesis test, and actually what you're going to see here is that for this really to work, for everything to perfectly come out t-distributed, you have to start off with the assumption that you are drawing from normal. However, often in statistics we do t-tests when we haven't stated that assumption that we're drawing from normal, and this isn't something that I'm going to be able to prove because I don't know how to prove it, but what I am told by statisticians is that even in the case where it's not the case that you are drawing from perfect normal, certainly if you're drawing from something that's almost normal, that's good, but even in cases where it isn't necessarily normal, t-tests are still a sensible thing to do often. I do not know the actual, regularity conditions that are required in order for it to be a sensible, in quotation marks, thing to do. But I am told that often it is a sensible thing to do, and that's why t-tests are so widespread in statistics. But here we're going to learn about the perfect case where truly it does come out t-distributed, your test statistic, and I think this will, even though it's not the full answer as to why t-tests are so ubiquitous in statistics, it at least gives you something of an answer, and I hope you'll find it satisfying. So let's begin then. So we're going to say that we have some stochastic process that we are investigating, and we'll call this x, and we're going to have the assumption that it is normally distributed with some mean and some variance, and we don't know what these are. And let's say that our hypothesis test is going to be about what this mean is, and we'll have our null hypothesis, which is that this mean is equal to some null value, which I'll just call mu0. That's some constant value that we've selected. And then our alternative hypothesis is that mu is not equal to mu0, so the two-sided alternative. And to decide which one is right, we are going to take a sample. So we're going to draw from our distribution here. So we'll have x1, x2, all the way up to xn. So we'll have n draws from our stochastic distribution. And then we're going to take the mean of these. So we'll take x bar, And if our x bar falls in too far an extreme, according to the null distribution, then we will reject our null hypothesis. So we will assume that the null hypothesis is true to start with. We will say, okay, mu is mu 0, and therefore we are drawing from mu 0 sigma squared, and it isn't going to matter that we don't know what sigma squared is, what is actually, but we're about to discuss that, but we're going to get around the fact that we don't know what sigma squared is. So we're going to start with the assumption that the mean is indeed mu 0. We're going to draw from it, from our distribution, we're going to calculate the mean, and then if the mean is, too far away from mu 0, then we will reject the null hypothesis and accept the alternative hypothesis. And in fact, I should say what our significance level is. So we might say we'll work with a 5% significance level. So our alpha level is 0.05. So we calculate our mean then, and let's think about what the sampling distribution for our mean is going to be. So the mean is then just these n things summed together and divided by n. So we know that when we sum n normals together, we end up with another normal. So we're going to end up with it normally distributed, and then let's just think about what the mean is going to be. It will be, remember, we're assuming the null hypothesis, so this is under the null distribution, or under the distribution according to the null hypothesis, under the null distribution. So thinking about this, so linearity of expectation, it'll be the expected value of x1 plus the expected value of x2 all the way up to plus the expected value of xn, all divided by n. All of those are mu 0, their expectations. So we'll get n lots of mu 0 on the top divided by n, so we'll get mu 0 will be the expectation here. And then variance now, we're drawing IID from our distribution, so we're assuming they are all independent, so the variance will then just be 1 over n squared times the variance of all of them added together. So each one of them has this variance sigma squared. We don't know what it is, but we're assuming it is some constant. This is classical statistics, remember, so we're assuming these parameters are set in stone. There are some true values to them. So we'll end up with n lots of sigma squared over n squared, so we'll end up with sigma squared over n. So that's the sampling distribution then for the sample mean. And what basically, or that's the sampling distribution if the null hypothesis were true. So now what we'll actually do is carry out the experiment. We'll get a sample, those should be braces rather than curly brackets. So we'll get a sample, little x1, little x2, all the way up to little xn. We'll work out our actual x bar according to this sample, and if this sample falls too far in the extremes of this distribution, so this is some normal distribution here, it might look like this, where this is supposed to be mu 0 here, and if we get, an x bar that's all the way up here, then that's probably too far in the tails of the distribution. We're doing a two-sided test, so we'll take the two tails where the area, if you add this area to this area, you get 0.05. If it falls in that critical region, we will then reject the null hypothesis because, this is too extreme, we will say, in this distribution, in this null distribution, for this null distribution to actually be correct. Now, so what would we now do? What would our test statistic be? So we take our x bar and we then want to get a standardized test statistic. So we'd want to subtract off mu 0, and we then want to divide through by the standard deviation of this distribution because we want to try and compare it to the standard normal distribution. So this is going to be our test statistic. Now, here's where the importance of t-distribution starts to come in. Let's say, firstly, that we did actually know what sigma squared is. Like, let's say this is first year statistics course and you are actually given what sigma squared is. Then you can do a z-test. So this is the z-test. We're not going to do this. We're going to change over to the t-test. But firstly, we have to understand what we would do if we did know what sigma squared is. So we then divide through by the square root of sigma squared over n, which is the standard deviation of this distribution. So this test statistic is now going to be distributed normal 0, 1. Just to convince you of that, think about this. So these are just constants. So when we take the expectation of this, this constant will just come out the front. This one's expectation will just be itself. So you'll get the expectation of this one minus the expectation of this one. This one's expectation under the null distribution is mu 0. So we get mu 0 minus mu 0, which is 0. Now let's think about the variance of it. This constant adding something, shifting your random variable along, doesn't change what its variance is. So this bit isn't going to change the variance at all, but this is going to change the variance. So we'll get this thing squared times the variance of this. So the variance of this is then sigma squared over n, and then we're dividing through by sigma squared over n, so we'll get 1. So this standardized test statistic then now is going to be standard normally distributed. So what we could then do is we take the x bar that we actually get from our sample, we take away this mu 0 value, and we divide through by the square root of sigma squared over n. And remember, I've said that suppose we're actually given what the variance of our stochastic distribution that we're drawing from actually is, and therefore we're only testing the mean. Then we would be able to actually do this, and we get some value, and then we can compare that to the standard normal distribution. So I'll draw another picture. So here is the standard normal distribution. Again, a bad picture. But again, we'd have a critical region. We'd have, if we were doing a two-sided test at the 5% level, then we'd want the 0.975 quantile up here, and we'd want the 0.025 quantile down here. And these two tails here of the distribution would be our critical region together, and if our test statistic fell in that critical region, so say it came here or if it came here, then we would then reject the null hypothesis and conclude that this was not the correct value for the mean of the distribution. Whereas if it fell in outside, in this part of the distribution, not in the critical region, then we would accept our null hypothesis and say, yes, it's perfectly reasonable that this data that we've got, this sample, was drawn indeed from the distribution normal with mean mu 0 sigma squared. So that's a z-test, and that's if you truly do know what the variance of your original distribution that you're drawing from is, but frequently we don't know that. So instead what we end up doing is replacing this not with the actual variance, we replace it with our sample variance. So we have got a sample that has been drawn from this distribution. We can work out the sample variance of this sample, and we can stick that in as an approximation for our true population variance. So that's what we're more likely to be doing in statistics. So our test statistic now, and this is where we go over to it not being a z-test anymore. So it was called a z-test because the normal 0-1 distribution is sometimes called the z distribution. The standard normal, z is used a lot for that. And our test statistic came out z distributed, hence why it was called a z-test. We're now going to go over to t-test because this altered test statistic where we stick in the sample variance there instead is now going to be t-distributed. And the whole aim of this video is I want to explain to you why it ends up t-distributed. So we're almost there now. So our new test statistic is going to be x bar minus mu 0, and now it's going to be divided by s squared over n. Now let's remember our definition for s squared, and this is where you need to start remembering what we did in the previous video that I told you at the start I wanted you to have seen, which was the importance of the chi-squared distribution. So, sorry, just had to have a little break there to check my phone. Let's continue. So let's remember how we defined the sample variance. So remember we defined it according to the Bessel correction, and this is important. We need to use the Bessel corrected sample variance, not the naive sample variance. So remember, I use this notation SXX for sample corrected sum of squares, and I'll just remind you what that is. That is sum from I is equal to 1 to n, where the sample size is n, and then I don't know whether I want to write it with big X's as a random variable or small x's. I'll write it with big X's as a random variable, so xi minus x bar squared. if you wanted to write out what it actually is for your sample, you just replace it with little xi and then little x bar, and that would be your actual value calculated for a concrete sample, whereas this is referring to the random variable sxx, where these are the random variables being drawn from the original distribution. So we take that sample corrected sum of squares and we divide it through not by n, the sample size, but by n minus 1. And remember that that is a clever thing to do because of the fact that this comes out under the assumption that the xi's are normally distributed, under the assumption that they're normally distributed with some mean, and obviously we're assuming under our null distribution that they are distributed with the mean mu0 and this variance sigma squared, and we're now saying we don't know what that sigma squared is, but it is some constant. So under that assumption, and I'm going to just replace that line for a moment, because actually it's not sxx, it's sxx over sigma squared is then chi-squared distributed with n minus 1 degrees of freedom, and we showed that in the subsequent, or the, sorry, not subsequent, the previous video, the prerequisite video. And that's the reason why it's so much cleverer to divide through by n minus 1, because you're then dividing through by the degree of freedom of this thing here. And if you remember the definition of the t-distribution up here, we need to be taking the thing that is chi-squared distributed and dividing through by its degree of freedom. So this is how it's all going to work. You know, what we've got here looks very similar to what we've got here. In fact, it is going to be that. And so we do need to be dividing through by the correct degree of freedom. This thing is chi-squared distributed with n minus 1 degrees of freedom, so we want to be dividing through by n minus 1. And that's what we've got here. There's a division. We could substitute in s squared with sxx over n minus 1. In fact, I think I will do that now. That square root of n, you might get confused about the fact that there's a division by n here. You might think that that's going to be the division by n that is relevant in that definition of the t-distribution. It's not. The square root of n is going to be needed up here to fix things up, to, you know, make it normal 0, 1, because remember, in the definition of the t-distribution, we need normal 0, 1 up here. So that's going to play its role up here, and it's this n minus 1 that's inside this that is going to be the bit that stays down here as part of the t-distribution definition. So let's now replace this then. So this test statistic is going to be x bar minus mu0, and then, as I just said, I'm going to take this thing that we've got on the bottom. We've got, you know, s squared, square root of that, over the square root of n. So we can bring that square root of n up to the top, which is what I'm going to do. So I'm going to have that up here now. So we've got square root of n, and then on the bottom we've got the square root of sxx over n minus 1. Another point that I need to say is something that we needed in the previous video on the chi-squared distribution, which we're going to need again now, and which I didn't prove then and I'm not going to prove now, which is that x bar and sxx somehow, by some miracle, I don't know how, I haven't seen this proof, but I am told that this is true, that these, certainly under the conditions that we've got, where the xi's were normally distributed, they come out independent to one another. And that's really important, because if you remember the definition of the t-distribution, we needed something on the top that was normal 0, 1, and something on the bottom that was chi-squared, and they needed to be independent. And this fact is going to mean that this thing that we've got on the top, which is a modified version of x bar, and the thing that we've got on the bottom, which is sxx, they are indeed independent. So we're needing that again. Right, so what do we need to do now? So we know not how sxx is distributed, we know how sxx over sigma squared is distributed, so we're going to need to bring in this sigma squared. Now, you might think this is a problem because we don't actually know what sigma squared is. It isn't going to be a problem because it's going to cancel. So we're going to do another major trick in maths. So in the previous video we did the trick of adding 0. In this video we're going to do the trick of multiplying by 1, so multiplying top and bottom by the same thing in this fraction. So we will multiply top and bottom then by 1 over sigma squared, I think is, actually no, 1 over sigma I think is going to be the right thing to multiply by. So we'll get then x bar minus mu 0 over sigma, which is some constant that we don't know, but it doesn't matter. And then on this bottom, if we're multiplying by 1 over sigma, we can bring it into the square root, and we'll then get square root of sxx over sigma squared over n minus 1. So hopefully you agree that this is okay, you know, hopefully you forgive me for this. So I've brought the 1 over sigma in here, and then I've rewritten it like this. You know, you would initially have it as sxx over sigma times sigma squared rather, times n minus 1, but then you can split that up like so, and the reason I've done that is because it's helpful to have these two things together like this. So let's now work this all out. So we know that this thing on the bottom, sxx over sigma squared, this is chi-squared distributed with n minus 1 degrees of freedom. We've then divided through by its degrees of freedom. Good, so that fits exactly what we want in order for the definition of the t-distribution. Now let's just think about the thing on the top. So we know how x bar is distributed. Under the null hypothesis, it is normally distributed with mean mu 0 and then variance sigma squared over n. If we then take x bar minus mu 0, that's going to be normally distributed with mean 0 and variance sigma squared over n. Now, we could rewrite this actually. We could rewrite it as x bar minus mu 0 over sigma divided through by the square root of n, because, you know, if you divide through by fraction, you'd flip them and you'd get the same thing as this. So this is division by this fraction, sigma over the square root of n. And then that's quite helpful to understand then how this is all going to fix up. So just copying the same thing out again. There we go. So now x bar minus mu 0 over sigma divided by the square root of n, that is then, you know, sigma over the square root of n is the standard deviation of this thing. So we've now divided through by its standard deviation, so that is now going to end up normal 0, 1. And because x bar and sxx were independent, all we've done, you know, is modify them with some constants, so that won't change their independence. So this thing here, which is normal 0, 1, is independent from this thing down here, which is chi squared with n minus 1 degrees of freedom. So you're literally dividing a normal 0, 1 distribution by the square root of a chi squared distribution with n minus 1 degrees of freedom divided by its degrees of freedom, and they are independent. So this test statistic now, t, is going to end up, therefore, t distributed with n minus 1 degrees of freedom. So not with n degrees of freedom, with n minus 1 degrees of freedom, because it's the same as this chi-squared distribution here, which had n minus 1 degrees of freedom. And that is how this ends up t distributed. So, as I said, up on the level of the z-test, if you truly knew what your variance was going into your hypothesis test, then you could do the z-test and your test statistic would then end up normal 0, 1. If instead you don't have that and you have to use the sample variance instead, incredibly, it still comes out as a fixed distribution that we will know, and it comes out as this distribution no matter what the actual true sigma squared is of the stochastic distribution that we're drawing from. That's what's incredible. This will work no matter what that sigma squared was. So our test statistic comes out Tn minus 1. Again, this is a symmetric bell-shaped distribution centered on 0, something like this. So what we'd do is we'd calculate this test statistic for our sample. So we'd need to find out what our sample mean is and find out what our sample variance is, where, remember, we're taking the Bessel corrected sample variance. Very important that you use the Bessel corrected sample variance. You would take off the mu 0 that you're given, calculate all of this, you'd get some number, and then you'd compare this to the t-distribution with n-1 degrees of freedom. You'd know what your n is, so then you've got this fixed distribution, and then you would say your critical region will be the two-sided critical region. We're working with a 5% significance level, so you'd want the t n-1 0.975 quantile here, and you'd want the t n-1 0.025 quantile here. Below that and above that would define your critical region, and if that test statistic that you calculated fell in these regions, then you'd reject the null hypothesis, say that's too extreme for the null distribution to be true, therefore this null hypothesis that mu is equal to mu0 must be false. Whereas if it fell in the sort of middle region here, outside the critical region, then you'd say, okay, this is fine. We don't have enough evidence to reject our null hypothesis with that sample. So there you go. That is an explanation of why this sort of test statistic, where instead of dividing through by the true population variance, you use the sample variance instead, why this ends up t-distributed, why it ends up t-distributed not with n degrees of freedom, but with n-1 degrees of freedom. And how the incredible thing that I find personally is that it works no matter what the sigma squared was, that the sigma squared ends up cancelling on the top and the bottom because it's involved up here and it's involved down here. So I think this is very beautiful. I hope you've found it beautiful as well. This, of course, is an extremely simple example. T-test becomes so much more complicated than this. But I hope that this will help you to understand why, at least, this distribution becomes involved at all. It at least paves the starting point for you to understand how to understand properly how t-tests work.